This is a railgun, the future of military-grade weaponry. And this is a less cool railgun, but it is the future of our physics grade.
The railgun is powered by a self-induced magnetic field that generates a magnetic force, propelling a projectile. Current flows through the wire, which creates a magnetic field through the circuit loop of the railgun. In the diagram, the induced force pushes the projectile to the left. However, given our project parameters, this force would be negligible, so we added an external magnetic field to amplify this force.
As shown, our magnets lay adjacent, with similar poles aligned, which causes them to repel one another. This system of magnets creates a field out of the page. In our equation, F equals L I cross B, it increases the value of B, the magnetic field, and therefore F, the force pushing the projectile.
Wow, look at her go. They grow up so fast. To create our railgun, we used aluminum foil for our rails, an aluminum rod for our projectile, and 3 6-volt batteries. We connected the batteries in series to create a total EMF of 18 volts. Additionally, we have permanent magnets to increase the magnetic field. We attached all of these components to a piece of foam board. To analyze the mechanics behind our railgun, we can use Tracker to plot our projectile's motion. We can find the acceleration, and therefore the force. Here, you can see a plot of our projectile's x component position versus time. We took a data point every 1/60th of a second.
This graph is of the derivative of the displacement points. It shows velocity, as velocity is the time derivative of position. We want to find the acceleration, which will be the line of best fit through the velocity time graph. The slope of our line is the acceleration, which, when multiplied by the mass of the object, will give us the approximate force applied to the projectile.
We found the mass to be 2 grams, and our acceleration to be 0.159 meters per second squared, which means the force on the projectile is 0.318 millinewtons by Newton's second law. Because F equals I L cross B, and knowing that the current is 6.3 amps and length is 5.6 centimeters, we can determine that the magnetic field is 0.901 milliteslas. However, these calculations assume that no frictional force acts on the projectile. We can find the frictional force by rolling the projectile without current flowing through the rails. We obtain an acceleration of negative 0.131 meters per second squared, and therefore a frictional force of negative 0.263 millinewtons. Accounting for this force, the true magnetic force is 0.518 millinewtons, and the true magnetic field is 1.64 milliteslas. And that's the physics of the railgun.